Okay, here's the plan for today. I'm going to describe and evaluate methods of distributing survey questionnaires, talk about the good and the bad things about what we call convenience samples. I'm going to talk about some rules of thumb for determining how big your sample should be at sample size, learn how to calculate internal consistency reliability, or what you'll see sometimes referred to as Cronbach's alpha or occasionally just alpha, practice interpreting correlation coefficients and multiple regression. There's lots of ways of administering surveys. I call your attention to electronic surveys, which are increasingly common. You probably get lots of emails about a survey you need to take. Happens all the time. I know I've gotten a lot, especially lately, from like every organization I'm a part of, asking how pandemic and countermeasures against it are affecting you or your family or any other thing. Mass administered surveys, that would be like if we sat down in this room and everybody in this room. If we were in a room together and I gave a survey to all of you together, individually administered surveys are exactly what it sounds like, and they're somewhat common for marketing research or for political polling. Not really political polling, more like political analysis. Mailed surveys are definitely uncommon, but still a possibility. And I mean, those are things that would come in your real literal physical snail mail. Face-to-face interviews are a way that you can collect survey data as well as ask more detailed questions as either a precursor or a follow-up. And again, fairly common in both marketing research and political science. And telephone interviews, which are increasingly uncommon. People just don't respond to them in a lot of the world. And things to consider, like the need for anonymity. This is one argument in favor of electronic surveys, since the researcher and the survey taker never see each other, although some people may be concerned about, exposing like their MAC address or IP, or especially their IP address. Shouldn't say MAC. Things like that. So how complex the questions are, like if you're asking very detailed, very complex questions, it may be better to have an in-person administration rather than a distance administration. The cost in general, there's no marginal cost for electronic surveys. Like there is an upfront cost for, like any kind of hosting platform, but you can send it to, it costs exactly the same to send it to 10 people as 10,000 people after that. Whereas, there are printing and mailing costs for most of all paper interviews. There's cost per telephone call for phone interviews, face-to-face interviews. The cost is in terms of the researcher's time, which if you're paying people to do this could be quite a lot. If you're conducting one-on-one interviews. Speed, again, electronic surveys tend to be fast, but individually administered surveys can be quite fast. The other methods tend to be much slower since they happen one at a time. Potential for researcher bias, again, anything where you're interacting with the survey taker as a researcher, you could be introducing an experimenter bias into that by subtly leading them, evoking responses, and respondents' motivation. And this one's complex. It could be, people are probably not going to come in to a location specifically to do a survey, but if you can catch them with a short survey, they might do it. Under normal circumstances with this class, people often collect the data by just sort of setting up shop in the lobby at JMSB and just asking people to take the surveys. And if you're set up in between classes in, say, the morning or the afternoon, it's no problem. But if you're kind of like trying to catch people right before lunch or at around 5 o'clock, they're much less likely to respond to you. Sampling, this is kind of the ideal. This box represents the total population. So the population is what we're trying to talk about. So if we're trying to talk about all JMSB students, it's everyone who's enrolled in JMSB as a student. we need a sampling frame. So we can't just, so especially when we're talking about somewhat more abstract populations, like if we're talking about the population of Canada. Well, what is the population of Canada? The sampling frame is the way that we operationalize the population of Canada. So the sampling frame is, say, everyone who is recorded, like say everyone who's recorded in the census as a resident or citizen of Canada. And as you can see, the way this picture illustrates, this box is not the same as this box. We lose, under almost all circumstances, we lose something in the sampling frame. So for instance, if we're looking, like if we're even talking about something as well defined as the student population of John Molson School of Business, let's say when we take, like say we use the student directory, the database of students. Let's say we take a snapshot of the database one day, and that's our sampling frame, and somebody enrolls the next day, or anyone who enrolls the next day, or any day after that, between when we took our snapshot and when we actually collect the data. Those people are not counted. They're not part of the population, or sorry, they're not part of the sampling frame, but they are a part of the population. And just to be clear, that's what we call over here, that's sampling frame error. That's, the ways in which our sampling frame does not fully and accurately, the way our sampling frame does not fully and accurately capture our population. Now, when we have our planned sample, this is the standard sort of, I always tend to draw this way. Let's call this sort of class, sorry, not this bad of an artist, but I am with a mouse. This is our population up here, and I just use this sort of awkward theta to represent whatever quantity we're interested in. If we're talking about the population of the United States, this might be the percentage of the population who will be voting for, let's just say Biden. Anyways, so this is the population. Theta up here is the quantity that we're interested in estimating. When we take a sample, this is, our actual planned sample. And again, if this is a truly random sample, what we've got here is just meant to be every single person in the population has an equal chance of being represented in the sample. And this can be complicated, right? So like with a very small population, so if we're just talking about the students in this class, when I select someone out, then, if I did sequential sampling, then, that person had a lower chance of being selected than the next person did, because, once I've already surveyed them, they're already done. So they're out of the population and into the sample. Whereas with an extremely large population, that happens, but the changes in the probability of selection into the sample are minimal. So again, this happens that there is random sampling error, and this is what all of classical statistics is built around, is this idea that your sample is in general not going to be exactly representative of the population. And so what do you do about that? Well, that's what statistical distributions are all about. What they're going to capture is the expected, if we have an idea of what probability distribution the quantity that we're interested in should follow, then we know the limits, the typical limits that our estimate should fall between given random sampling error. Now, importantly, that doesn't capture the idea that there might be systematic sampling error, right? That, if our sampling plan is unrepresentative, so let's say we've overrepresented affluent white males in this example up here, well, we might get a lower percentage of people planning to vote for Joe Biden in the US election than we might otherwise. And then we get the actual sample. So this is the sample that we plan. So this is, let's say we have our sampling frame. A lot of times what we would do is to get our random sample, what we do is just generate a random, let's say like a uniform random variable between 0 and 1, and if you were above, say, 0.5, you were in the sample. That would mean that every person in the sampling frame had a 50% chance of being in the sample. We could do it differently if we wanted a smaller sample, we would say, like, if we wanted 10% of the sampling frame to be in the population, we'd do that, and we'd say if your random number was 0.1 or below, you are in the sample. So that's just, that's just an operational hack, but that's the planned sample. When we go to give that survey, like let's say we email it to people, not everybody responds. And this is analogous to exactly what we're talking about with the electronic course evaluations a few weeks ago. Not everybody does them. Some people do them sometimes and not others, and it depends on a lot of factors. So people might get our email or our mail or our phone call, or we knock on the door and they say, I don't have time for this, I'm not interested, please stop bothering me, or any of those sorts of things. So that's non-response error. So the basic idea here is sampling frame. Sampling frame error is the way in which our sampling frame, which is our operationalization, so like how the actual people that we're going to count practically as part of the population, the ways it differs from the total population. And that can be systematic, right? Like any way that we would want to talk about it. Like if we're talking about, again, the population of Canada, the sampling frame that we have for that is going to systematically underrepresent, say, homeless people, first peoples, all of those sorts of things, because they're less likely to be represented in any kind of census data that we would use to represent the population of Canada. So the sampling frame error is like, and the same sort of thing is people. This is not necessarily well, it's probably systematic. My example with the John Molson students, that anybody who was registering relatively or enrolling relatively late is probably different from the students who were enrolled earlier. Random sampling error, that's just what happens. Like if we're randomly sampling people from the population, some samples are going to be more representative than others, and that's just the way that it works out, and that's what statistics is built around. The non-response error is just sometimes when we go to talk to people, they say no, and they're not interested, and they're not going to do it. Interestingly, in the comparison that I'll make here is between the United States and Canada, and non-response error, non-response bias is quite high in the United States. People are not interested in doing surveys, whereas if you compare that to, say, Germany, people are like, would you like to take a survey? And the response is, yeah, yeah. Like response rates are around, like broad-based surveys in Germany are typically 85% and above, whereas response rates in the United States are around like 15% and less. Up until now, I'm not sure if maybe people might be taking more surveys just because they're bored because of being at home a lot more. Anyways, this is still the ideal. The actual is that we usually have a convenience sample. Let me just erase some of this. And what do I mean by, oh, no, come on. Sorry, it's getting sticky for some reason. I don't know, there we go. So when I say convenience sample, what I mean here is that, especially in management research, our sample is not usually of any particular population. It's, maybe students in a particular class. So here at JMSB, if you're taking this class, you should have already taken COM222, and that's a subject pool. Like if you're enrolled in COM222, you're part of that, and a lot of people take any studies that are there for extra credit. That's not a random sample of anything. I mean, it's students who take COM222, which is, I think virtually everyone in JMSB but not everybody does the surveys. Some people just choose not to. Some people opt for the alternative assignments and things like that. So, and it's not like John Wilson students are representative of any particular thing. Like they're probably not too different. You guys are probably not too different from students in any other business school, but you know, you're probably more similar to um, students at McGill or HEC, since you're going to, you know, schools here in Montreal, than you are to students at maybe Harvard Business School or, you know, the Culverhouse School of Business at University of Alabama. But then again, you know, Desautels students are probably more similar to HBS students than you are, just because of the way the schools work. So yeah, you're probably not drastically unrepresentative of business school students everywhere, as a sample at least, but you're not the same. So it's hard to generalize to say business school undergrads from a sample of Concordia students. Not impossible, and people will talk about that. But this is something that's often winds up being addressed in limitation sections, is the ways in which the sample is maybe not representative, and that future research could look at a more representative sample or something along those lines. But in general, in management research, a lot of times we are going to end up surveying organizations that we have access to, either because they have a particular problem and have reached out to a particular researcher to work as a consultant. I've done that many times. I've consulted for a couple of organizations. Headhunting firm in New York. It's an executive search, if you're not familiar with the term, although I suspect most of you are. And a power distribution company in Peru, amongst a couple of other sort of organizations. And you know, when working with those kinds of organizations, researchers will often at least attempt to collect data. Doesn't always work out. Like the data was not of any kind of quality with the company I did worked with in Peru, and there are reasons for that we may talk about later on. So the issue here is that using substandard samples has implications for external validity. That's kind of what I was talking about when I mentioned that this is something people talk about in the limitation sections of their research papers, is that, you know, since if the sample that you're actually using for your statistical hypothesis tests is not representative of the population that you would like to generalize to, what can you do? And again, I want to be clear, in practice, that doesn't stop anyone. But we do need to appreciate that in reality, you know, if you're, you know, it only works to talk about, like, again, if I survey, like again with the US election example, if I did a survey and only did a survey of registered Republicans, I would probably have a very, very, very low estimate of the percentage of people who will vote for Joe Biden in that example. Like probably not zero, because registered Republicans and registered Democrats vote for the other side regularly, but it's a very low percentage, like 8% or less. Whereas national polling, you know, I don't want, well, maybe as an American, maybe I don't want to talk about this. It's depressing. Um, but here's just an example of a question or a questionnaire survey that you could look at. Measure of financial anxiety. How strongly do you agree with each of the following statements? So with 1 being strongly disagree, going up to 4 equals strongly agree. And this, you know, if we haven't described it before, this is what's called a Likert, or more properly, Likert type scale, named after Rensis Likert, one of the earliest organizational survey developers. And so it will typically be on a scale of agreement, although it can sometimes be just in terms of satisfaction. So usually ranging from strongly disagree or strongly dissatisfied to strongly agree or strongly satisfied, although you can flip those around. So 1 could be strongly agree and 4 could be strongly disagree here. there are sometimes reasons to do it one way or the other. But here's the questions. I have plenty of money to do the types of things that I enjoy. Strongly disagree to strongly agree. With my current income, I have no trouble making ends meet. Strongly disagree to strongly agree. I feel anxious about money. Strongly disagree to strongly agree. I have sufficient income for my wants and needs. Strongly disagree to strongly agree. Now, again, with a sample of undergraduate students, you're probably going to get very different answers than with a sample of, mid-career adults. So especially mid-career professionals, that as someone who's at least rapidly approaching mid-career, I would have to say pretty much strongly agree to 1, 2, and 4, and strongly disagree to 3. And this is something to note. This here is what we call, oh boy, see how well I can write with my mouse. Oh, it looks like my kid's writing. Reversed. I'm going to call it just reversed so I don't have to write more. But we would call reversed score, reverse scored or reverse coded typically. So in the idea that the positive fraction or the everything else this is more a measure of financial security or subjective financial security, and that 1, 2, and 4 are all about if you agree with the statements, you are not financially anxious, where this one, if you agree with it, you are financially anxious. So these are different. So let's just say this is a 4. So this is what I'm going to say here is k equals 4, because there's 4 options here. And if you do general, what you're going to do to reverse this is to have k plus 1 minus the response, which I'm just going to call resp. Or, Jesus, I should probably just call it x. And that's going to give you the reverse score. So for this one, if you answered 1, you would have k plus 1. So that's 4 plus 1, that's 5 minus 1. So 1 becomes 4. So if you strongly disagree with this item, it's equivalent to strongly agreeing with the other 3 items on the scale. And there's good reasons to have reverse scored items like this, in that it allows you to check data quality pretty quickly. So for instance, let's say like if someone goes through and says 4 here, 4 here, and 4 here, they should probably say no more than a 1 here. But if they say also put a 4 here, this is at least an indication that they're not really reading the questions. This is one way to check. Reverse answer. So in general, like when we want to calculate, as we go on later on, when we want to calculate Cronbach's alpha, we need to reverse score items before calculating that. And generally, and also before, like if we want to make a scale variable out of this, or what we sometimes will call an index variable, you need to reverse these before you sum or average over the items. Otherwise, this item will essentially, like, quote unquote, count against the score. Do you think that in general, well, actually, these sort of talk aloud things don't really work here, but just think about whether or not the average financial anxiety scores given by people in this room will generalize to the population as a whole, and think about why or why not. Because that's the thing, like if we use you guys as a sample, you are a convenience sample. Like I have access to you. And so if I want to say something about like, oh, people are so anxious about money, or maybe the other way around, depending on how you actually respond, it might be that does not necessarily reflect the population. This is just an example of a selection or sample selection approach. So the sampling frame is using Canada 411 online, and so they divided Montreal up into 3 sections. So Montreal Island Center, Montreal Island East, and Montreal Island West, and then just randomly chose to use the East section, and then within that broke that into neighborhoods and chose Anjou, Saint Leonard, and Montreal, randomly selecting from there, and then used what's called a snowball sampling technique. So the basic idea here is they approached, these were all bakeries, right? So they approached 75 bakeries and 31 owners responded. That's a 41% response rate. So that's pretty low. And then from those 75 firms, they approached 300 employees and 96 employees responded. So amongst the employee response rate was 32%. So of that left us with participant owners. There were 25 men, 5 women, and one was missing after this. And 8 owners were French speaking, 23 owners were primarily English speaking. The participants from the employee side were 37 men and 59 women. 36 employees were French speaking and 60 were English speaking. So, so the snowball part here is this idea, and this is something people talk about in looking up references as well. So snowballing is a relatively general technique, but you find something like a sample or a paper, and then you use that to contact others. So like I contact a firm, like a firm, they agree to participate in the survey, and they give me contact information for their employees. This is similar to, and this is done a lot in organizational studies in general. So I might contact a group of employees and have them provide contact information for, say, their supervisor, or the other way around. I contact a bunch of supervisors and have them provide contact information for their employees. So I can try to survey both the supervisor and the employee, and that can be very, very useful if you want to do research on, say, leadership or teams or something along those lines. The survey distribution technique. So the owner completed the owner's questionnaire, and 1 to 5 employees at each firm completed the employees questionnaire. And employees questionnaires were given to the owners, who then distributed them to their employees. And employees returned the questionnaires to the owners in sealed, unmarked envelopes. And so that last part is there to try to protect anonymity and confidentiality. So the owners are not supposed to see the responses that the employees gave to the surveys. That's why they seal the envelopes, and the owners would be in ethical, like the researchers would not be in ethical trouble if the owners opened those envelopes, but the owners would be. But there's potential problems here, right? Like could the employees distributing their own questionnaires to their own employees cause potential bias here? Like what if they gave them to their favorite employees, so that there's like quasi nepotistic bias in the employee sample. This was definitely not, even though, if we went back, we'd see, it's hard to go back here. But anyways, if we went back, you'd see that, yeah, no, this is not a particularly random, even though it started off with, dividing them on the island up into 3 sections, randomly choosing one of them, randomly choosing neighborhoods within that section, and then randomly contacting employers within those samples. Certain between the relatively low response rates from both the employers and the employees, that's already affecting whether or not this is random, because of selection. Like those are selection effects, and there's also the issue that, well, just in general, the employee sample is not going to be randomly selected because the employer decides who gets it. These are the rules of thumb about sample size. Now, in general, if this were a statistics class, I would probably encourage these to be much larger than these rules of thumb. But in general, these are old rules of thumb. As you can see, this is coming from a paper from 1975, which is even older than I am, which is getting increasingly surprising. But these are guidelines that generally work. Sometimes the low end of this may not be is not generally regarded. So sample sizes larger than 30 and less than 500 are appropriate for most research, and that's probably true depending on your definition of most. I would be hard pressed to encourage sample sizes of less than 60, and honestly, probably more than 100 would be sort of my minimum. In fact, I would tend to think like a sample for most research in management, a sample size of 120 would be ideal. So something 4 times larger than the minimum here. But again, as far as it goes, know these guidelines. Just I'm warning you that if you do go out to do research, like in any sense professionally, you may run into some problems with the low ends of these, where sample sizes can be already broken down into groups, like male versus female. A minimum of 15 per group is necessary. And again, this is maybe true in really, really well-controlled experimental research. So these guidelines are kind of being heavily influenced by cognitive and behavioral psychology, and in those, like I've seen like really excellent research, like with neurological mapping research of people doing tasks like EEGs of people doing a day trading game. Had a sample size of 4, but that's extremely expensive research, and it's very, very precise and incredibly tightly controlled. So again, smaller sample sizes are probably good when you have tight experimental control, but within a survey setting, I'd be hard pressed to say less than 30 people per group. But again, the traditional guidelines are, this is right for traditional guidelines. And in multivariate research, so if you're doing like a regression analysis with multiple, like 3 or more variables involved, then the sample should probably be at least 10 times larger than the number of variables. And in fact, that's probably, again, probably an underestimate. A lot of times it's going to say, the idea here is that it should probably be 20 individuals or 20 samples per variable. And if you were doing something more intense in multivariate research, like something called structural equation modeling, which involves lots of paths, like in a boxes and arrows diagram, it's generally said 5 individuals per path, and that will typically have a lot more paths than just a regression model or the kinds of boxes and arrows diagrams that we've done so far. And again, in tightly, like as I implied earlier, that tightly controlled experimental research can have much smaller sample sizes, and the guideline here is 20. Again, this is 20 individuals, right? Or at least for the kinds of purposes that we're talking about here with survey sampling. Now here, this is an example of a positive correlation. This is a perfect correlation. So energy level today, hours spent socializing over Thanksgiving weekend. The basic idea here is that if this is a perfect correlation, this line is going to be on the 45-degree axis for these two variables. So it'd be perfectly correlated. The more time you spend socializing, the higher your energy levels are today. And this is a perfect negative correlation. So empathy for the homeless and annual take-home pay, this would be perfect. And again, this is basically, if you just invert things, this is the negative 45-degree. This is just a straight line, and the basic idea here is what we're doing with positive correlation. So I'm just going to put a plus here, is X is proportional to, that perfect correlation is that X equals Y. And with a negative correlation, X equals negative Y. Like, that's perfect. These are perfect correlations. So a correlation of 1 or -1 respectively that's what so perfect. So you could think about it, that exact line where X equals Y or X equals -Y, or Y equals -X, whichever way you want to think about it. I'm just going to put a bar here so that nobody gets confused. So it's not like, it doesn't look like it's -X equals -Y and confuses people. So that's what's going on here. This is no correlation between variables, and this would just be a flat line, or at least as flat as I can make it under these circumstances. A lot of times, if I'm doing this in the abstract, I would just draw this as kind of a circle, because the idea here is that, basically all we know here is that X does not, well, even that, no. But basically the idea here is that X tells us nothing about Y. If I know your X variable, so if I know the distance you travel between home and school, it tells me nothing about your GPA. You can have a very high GPA, very low GPA, mid-high, mid-low, exactly average. It tells me nothing in this example. So the basic idea here is that the line here would be that X is perpendicular to y. Like there's just, well, nah, that's not even right. That's not even right. That's not the right way of saying that. Like we might write it here that x is double bar 1. If you, like in a certain brand of statistical nomenclature, that's what we would say is x is perpendicular, or not perpendicular, but x is independent of y. They tell it, like, knowing x tells us nothing about y, knowing y tells us nothing about x. What about this correlation? Give you a minute to think. Well, in general, this would be like, conceptually, this is just 0. Now, in general, because this is a sample, depending, like if there's more over here, it might be a little bit positive. If there's more samples over here, it might be a little bit negative, but they're all going to hover really closely around 0, even though this is a perfect relationship. There's no variability around this. These are just sampled points from a parabola. And so that's the thing to remember, is that correlations are, oh boy, gosh, linear. They only capture information about the line that you can draw amongst these dots. So the fact that this is a perfect relationship, it would still have a near a conceptually 0 correlation, or at least a near 0 one in practice, because the relationship is not linear. It is curvilinear, and correlation does not directly capture that. Now, you can represent the relationship on this in a correlation metric by fitting what's called a polynomial regression. So in this case, something like y equals b, oh boy, b's are hard, b0 plus b1x plus, oh boy, b2x squared. Now, this regression would fit this, and you could get the multiple regression coefficient out of it, the capital R, and that would tell you what the linear relationship between this equation and y is. Not between x and y, but between that equation, which tells you how predictable, since x is the only independent variable involved, it would tell you how predictable y is from x, and that's perfectly. And don't worry too much about that. We can talk about that. In fact, this is probably above your pay grade, but it's the important thing here is this is why you should always look at your data. You should, like, if you're really doing statistical analysis, you should look at these are called scatter plots, when we plot, x versus y, and the data points, every xy pair for every individual in the sample as a point in that plane. It's called a scatter plot, and it helps you to see, how strong the relationship might be, if there were any obvious irregularities, outliers, non-linearities like this. So it's if you're doing serious statistics, it's an important thing to do. So in this case, like the correlation that I got by plotting this was, as I said, close to 0, not exactly 0. And again, it's because kind of like the upswing has a little bit more data in it randomly. This is purely, these are just random, like this, I just randomly generated an X and then like ran it through like, I think it was 100 X's and then just squared it here. So it's a perfect parabola. Testing hypotheses, and this may be, I'm going to post some additional video because I'm not sure that I covered this very well. So expect maybe tomorrow, but probably Thursday. I'm going to post some additional. In fact, I will post some additional material talking about levels of measurement today, but I'll put some additional slide lectures as soon as I'm able, which should hopefully be Thursday morning, if not sooner. So testing hypotheses, associations among continuous variables. So we use the correlation coefficient when there are two variables. So this is so the difference between correlation and regression is similar to the the status that we talked about in class about the difference between a t-test and an ANOVA. So when we have the correlation coefficient is when we have two continuous variables and they're continuous, so they're interval or ratio measured, each one of them. Then if there's only two of them, you would typically do a correlation between them to measure the strength of their linear relationship. Now, it's not going to stop you from doing a simple regression. Like, you actually want to know the equation of the line, the best fitting line between them. You could still do a regression here, but it's going to give you exactly the same, like the multiple R, the capital R that comes out of that regression is going to be equivalent to the standard regression coefficient. That's the Pearson's regression for, like, when we get to looking at JASP, the Pearson is the standard measure. Use multiple regression when there is more than one independent variable. And so basically the idea is we're going to use multiple regression if we have a 3-variable system with 2 independent variables. And there, again, all of the variables are interval or ratio. And again, so notably the dependent variable is interval or ratio. And as I noted a few weeks ago when we were talking about the course evaluation example, this is just the pay grade that we're dealing with here. There are techniques, well, in fact, there's nothing special about doing multiple regression with, say, nominal or categorical independent variables. It's just interpretation. You have to code, like, the numbers you choose to represent each category have to be specially chosen in order to make the results interpretable. But there are special techniques for doing, there's various techniques, particularly something called generalized linear regression for dealing with outcome variables that are not continuous. Probably the most well-known being logistic regression, where you have just one of two categories, or two categories as the outcome. And then the other well-known one is Poisson regression, where the outcome variables are the counting numbers. So like when your outcome variables are, technically you could adjust it to work with integers, but typically it's the natural numbers. And there can be some cases, like depending on what's going on, you may or may not be able to include 0 as one of them in the software that you're using, in which case people just usually add 1 to everything, so that 0 becomes 1, 1 becomes 2, and so forth. But again, you shouldn't waste your time with that. You don't need to know it. If I had editing, I would probably take most of that information out, but just know that you're not limited to this. Data transformations, we'll see this more in the live session, but when several in-question items are used to measure a single variable, so a single conceptual variable, we usually take an average of those items to represent each participant's score on that questionnaire scale, and that's called an index. So if there are reverse scaled items, you flip them around, you change them so that everything's essentially quote-unquote pointing the same way. You check its internal consistency, reliability, so you calculate Cronbach's alpha, and then you calculate the average score for the variable. And I will show you how to do that in JASP later on. You have to stop, go back, and then re-record. So down here we've got, since we've got const 1R and const 3R, those are reverse scored items. So we would take them from the normal scaled items and put them over here in the reverse scaled items. And just to give you a preview of how JASP works. And that gives us a Cronbach's alpha of 0.64 and some other information about it. I'm not reporting the mean, like I'm not giving you the means and the item rest correlation just yet. Here they are. So the basic idea here is that what we can see is this const 3R is not a great indication. Like it's got a lower, like the rest of them correlate with each other about, nearly 0.5, at least 0.4 in all cases. This one's under 0.4. And what we can see here is, like, in general, if item dropped, this is just telling us what the Cronbach's alpha would be. So we can see here, if we drop item 1, it goes down. We had 0.64, it goes down. If we drop item 2, it goes down. If we drop item 3, it goes down. But if we drop and again, the reason why all of these are lower is because it's only like what we would be looking at is a 3-item scale, which is typically going to be less reliable than a 4-item scale. And again, it's not that this, and like if this item was, if we hadn't put it in the reverse scoring and so it correlated negatively with everything else, this would be a much different. It would be a much worse item, and we'd see much bigger differences here. But just in general, the idea here is if we take this, it says that the Chromebox Alpha would go up relative to the others. So baking fever, the low reliability of the affective commitment measure. So the reliability of the affective commitment items was found to be 0.56. This is lower than the reliability found in past research, which was between 0.85 and 0.87. The low level of reliability meant that we had to remove this measure from our analysis. So that's the idea. Like, the idea here is like, if you had a scale that fluctuated. I mean, like think about when you're trying to either like say if you're dieting, maybe you're trying to lose weight. If you're lifting weights, you're maybe trying to gain weight, and so you want to measure yourself at the same time every day and under the same circumstances. So maybe like after you've done your business in the morning, but before you've eaten breakfast, because that's going to help you track what your actual body weight is. And that's why. But whereas if you like some days measure yourself after breakfast, some days before, sometimes late at night, sometimes your weight might bounce all over the place, not because you're truly losing or gaining weight, but because of the differences in the circumstances. And that's the idea here is like a reliable scale is similar to weighing yourself on the same scale at the same time under the same circumstances. It's going to give you a consistent measure of what your true weight is. Whereas this one, I think an unreliable scale is not. So that's important. And in general, we've got the indication that really. I mean, a Chromebox Alpha should be above 0.7 to be considered reliable enough for doing research. Now, sometimes people will make some arguments that with really experimental or like untested surveys, like you can start doing initial research if the Chromebox Alpha is like maybe in the 0.6s. But in general, 0.7 is where you really want to be. And if you're going to like in HR, if you're going to be making decisions based on some sort of a multi-item scale, you usually want them to be very reliable, like 0.9 and above. So those are the indications. So again, just like always, like levels of significance, we're going to interpret in the same ways as we've talked about before. Like if p is less than 0.05, yep, this is statistically significant. If p is greater than 0.10, it's definitely not significant. And if it's between 0.05 and 0.10, it is marginally significant. And, the same caveats apply that I talked about in class, a couple of weeks ago, that, some people say that 0.05 is actually too high and we really want 0.01 or 0.05. 0.01 or 0.005 even. But these things are basically accepted in management research. This marginal issue is the one like that people will often get a quote unquote get away with talking about marginal significance, but for those of us who are sort of sticklers about statistical significance, that's unacceptable. But for the purposes of this class, you can do it. So if you conduct a statistical test and it's between 0.05 and so you get, say, a p-value of 0.07, you can talk about that as being marginally significant. So here's the example. So here's a correlation matrix, and again, like the basic idea here is each one of these is just the correlation between satisfaction with university item 1 and satisfaction with university item 2. So those correlate 0.55, p-value is less than 0.001. Same, the interpretation is the same here, except this is correlation of USAT1 with USAT2, USAT1 with USAT3, and this is the correlation between USAT2 and USAT3. And you can see it's got the dashes along here because these would be the correlations and p-values of the items with themselves, which, from the idea that x equals y is perfect correlation. Every one of these is, since it's x equals x, the correlation between of an item with itself or any variable with itself is always 1, which is going to have a p-value of exactly 0. So as you can see, like this is a pretty good scale. The items hang together really well. They are all very significant. So then like this is at the limit of the way that JASP reports things. So it is less than 0.001. So these are highly significant. This is honestly I guess the idea here is we should just look at this for honestly, these are this one, this one, and this one, and this one are independent variables. These are all continuous variables, all at least interval or ratio measured. In fact, age, marks in school, and years of education are ratio. Level of intrinsic motivation is, we'll probably call it interval. It might be ordinal in reality, but we'll just call it interval. Level of job performance, this is probably going to be an interval scale unless it's something like sales. And again, this is what we're talking about. It's unclear what we're talking about. To be comparable across jobs, this is probably going to be some measure of supervisory rated satisfaction, or at least that's the way most researchers would design it. And it is a mediator. Perceived usefulness of past education. This is a second mediator and would again probably be an interval scale since it's a perception. And interest in returning to school. This is our dependent variable. So this is a multivariate setup with 1, 2, 3, 4 independent variables, 2 mediators, and 1 dependent variable. Hypotheses, we can break this apart and test hypotheses with bivariate correlation coefficient. So we got H1 equals the level of job performance and perceived usefulness of past education. H2 is the perceived usefulness of past education with interest in returning to school. And age is hypothesis 3, directly predicting interest in returning to school. Hypothesis to be tested with regression analysis. So we have 3 independent variables, and in this case, although in the overall model this is a mediator, we can treat it as a dependent variable for this analysis. Level of job performance being predicted by years of education, marks in school, and level of intrinsic motivation jointly. That's H4. And so this is what a regression analysis looks like. So it starts off with a model summary, and so what we're really concerned with here is R, or R squared, really R squared. Sorry. R, this is just, like I said before, this is the correlation of the entire regression equation with the outcome. So we sometimes would call this maybe y hat, where y hat is the actual regression with like all the b's and x's and whatnots. R squared is the variance explained. So you can say this like 3% of the variability in y is explained by the regression equation. And then each one of these is going to come with, like every regression also produces an ANOVA table, which is interpreted just like the ANOVA, like a regular ANOVA, although instead of like a model or with sum of squares within, it's just the regression, which is our model, and the residual is the unexplained stuff. So we've got an F equals 3.17. We should round down with a 4, and a P of 0.04. Rounding down. So again, this overall regression model is statistically significant, and the R squared is 0.03. So that's what we would these are the first pieces of information that we would report. So like again, R squared is telling us like overall how well does this regression equation explain or predict the dependent variable? And the F test and its p-value is telling us, is the regression overall statistically significant? So if the regression overall is not statistically significant, we pretty much wash our hands of it. There's no statistical evidence that this regression model is doing any work predicting the dependent variable. So we wash our hands of it. Whereas it's statistically significant, then we move on to looking at the coefficients. And here, this is poorly formatted, but here we go. This is the unstandardized coefficient, which is all you'll ever need to worry about in this case. So here we're looking at the intercept. You never really, in fact, actually no. Sorry. That's me being dumb. We'll talk about the standardized coefficient because there you don't have to worry about the intercept, which is the beta 0 or b0 and everything that I'm talking about. Here we're just going to report our standardized coefficient, which is honestly pretty similar to a, I mean, well, you see, like it's a transformation of a t. It's a t-distributed variable. This is just essentially the ratio of the standardized unstandardized coefficient to its standard error. Don't worry about that because you don't need to worry about the t in reporting here. You're just going to report if the regression is statistically significant. You'll report its standardized coefficient, preferably to 2 decimal places. So here we've got the conscientiousness in the regression that I ran here. This is a significant predictor, but openness, these are both personality variables, the coefficient is very, very small. It's less than 0.01, and it is massively not statistically significant. 0.96 is way bigger than 0.1. So that's the idea here. So overall, the regression model is statistically significant. It predicts about 3% of the variance in our dependent variable, and virtually all of the work is being done by conscientiousness. It is statistically significant, whereas not only is openness not statistically significant, it is a trivial coefficient. It is so close to 0. So it's as close to 0. What I'm saying is it's almost a flat line, right? Like going back to those diagrams earlier. And so there we go. Those are the things that we need to worry about reporting. So that's all I have today. I'll get this up as soon as possible. Thanks so much, and see you soon.